Student, we know that according to Kohlraasch law, the limiting molar conductivities of an electrolyte can be represented as the sum of the individual contributions of anions and cations of the electrolyte. Okay, student? In general, if an electrolyte on dissociation gives new plus cations and new minus anions, then its limiting molar conductivity is given by, this is the limiting molar conductivity, and it is the sum of the total molar conductivities of cations and anions. Okay, sum of the total molar conductivities, limiting molar conductivities of cations and anions. This is cation and this is anions. So according to Kohlraasch law, limiting molar conductivity of an electrolyte can be represented the sum of the, this is the sum of the individual contributions of anions and cations. Okay, student, here lambda plus and lambda minus are the limiting molar conductivities of cations and anions. Okay, student, for example, molar conductivity of acetic acid. This is a weak acid. At infinite dilution can be obtained from the knowledge of molar conductivities at infinite dilution of strong electrolytes like HCl, CH3COONA and NaCl, such as limiting molar conductivity of CH3COOH, and the sum of CH3 cations and anions. Okay, and this is written as CH3COO minus plus Na plus. Okay, and H plus we get from HCl and minus lambda 0 Na plus and Cl minus. Okay, so that is CH3COOH equal to molar conductivity of acetic acid equal to sum of the individual molar conductivity of the sum of the individual components, that is cations, molar conductivities of the cations and anions in the electrolyte, minus molar conductivity of NaCl. Okay, student. So we molar conductivity of acetic acid. This is a weak acid. At infinite dilution can be obtained from the molar conductivities at infinite dilution strong electrolytes like HCl, CH3COONA and NaCl. Okay, and we can write in this way: all are broken into their corresponding cations and anions. Okay. Now student, degree of dissociation. Degree of dissociation, that is alpha equal to limiting molar conductivity by molar conductivity. Limiting molar conductivity by molar conductivity. Okay. Now student, we discuss about cell diagram or the representation of an electrochemical cell. Okay. Now we write here a representation of Daniell cell. Daniell cell written as Zn 2 plus Cu 2 plus C2 and Cu S. Okay. Student, this is a representation of a Daniell cell. Okay. Here anode half cell written on the left hand side. This is anode half cell and this is cathode half cell. Okay. And a single vertical line. This single vertical line separates the metals from their electrolytes. Okay. A single vertical line separates the metal from aqueous solution of its ions. Okay, this is the aqueous solution of the ions and separated by Zn by a single stroke. Okay, and a double vertical line. Here this is the double vertical line represents Sol bridge, which allow the passage of ions through it but prevents the mixing of two solutions. Okay, and the molar concentration, these are the C1 and C2 here are the molar concentrations, is placed in brackets after the formula of the corresponding ion. After the formula of the corresponding ion, we write the molar concentrations. Okay, here C1 and C2 are the molar concentrations. The value of EMF of the cell is written on the extreme right. For example, Zn2 plus and its 1 molar concentration, Cu2 plus 1 molar concentration solution, Cu, and its EMF equal to plus 1.1 volt. So EMF written on the extreme right side of the cell structure. Okay. Now in the if an inert electrode like platinum is involved in the construction of the cell, it may be written along with the working electrode in bracket. For example, when a zinc anode is connected to a hydrogen electrode, we can write it in this way: Zn2 plus its molar conductivity, then double stroke H plus C2 H2. Okay student, we write in this way. Clear? Student, electrode potential. What is electrode potential? It may be defined as the tendency of a metal when it is placed in contact with its own ions to either lose or gain electrons. Okay, and in turn become positively or negatively charged. The electrode potential will be named as oxidation or reduction potential depending upon whether the oxidation or reduction has take place. Okay, so electrode potential written as oxidation and this is reduction. Okay, then amine plus an aqueous solution in E, or it can be written as plus in aqueous plus in E minus, also oxidation and reduction, oxidation and here reduction, that is MS. Okay, and its special characteristics such as both oxidation and reduction potentials are equal in magnitude but opposite in sign. Okay, and the reduction potential shows an increase with increasing concentration and decrease with decreasing concentration of ions in a solution. Okay, and it is not a thermodynamic property, so values of E are not additive. Okay, student, now we discuss about Nernst equation. Okay, Nernst equation. We write here Nernst equation, that is E cell equal to E0. This is student, this is Nernst equation. Okay, and it can be written as standard cell minus RT NF ln concentration of products, molar concentration of products by molar concentration of reactants. Okay, molar concentration of products by reactants. Now substituting the values of R and F, we get E cell equal to standard cell minus 0.0591 by N. We put the value of R and F. Okay, and this is 0.0591. Okay, in log of molar concentration of product by molar concentration of reactants. Okay, and this held at 298 Kelvin temperature. Okay, so at 298 Kelvin temperature, Nernst equation is this. Okay, this is the Nernst equation. Okay, student. Now we establish EMF and Gibbs free energy with a relation, that is E of cell equal to E0 or standard EMF of the cell, and we get delta Gibbs energy, standard Gibbs energy minus NF standard EMF of the cell. So student, mathematically we know that the work done by a reversible galvanic cell is equal to the decrease in its free energy. Work done by a reversible galvanic cell is equal to decrease in its free energy. So mathematically we can write it Gibbs energy minus NF E of the cell. Okay. Then E of the cell, total EMF of the cell, that is if concentration of all the reacting species is unity, if concentration of all the reacting species is unity, then we can write this equal. Okay, standard EMF equal to EMF of the cell. So we can write then Gibbs energy in this way. Okay, from delta G we can calculate the equilibrium constant of a reaction. Okay, by in this way, minus RT ln Kc or del R G minus 2.303 RT log of Kc. Okay, student. So we can write EMF and Gibbs free energy. Okay, in this way. Okay, student.